Hey guys, welcome back. This is our second set of notes for chapter 16, which is acid-base and solubility equilibria. We left off last time with titrations. This is something you've done in Gen Chem and AP Chem a little bit, so we kind of have a pretty good idea of what you're doing in a titration, but this is where we're going to start. So in a titration, we take a solution where we know the concentration, and we add that gradually to another solution of unknown concentration until the chemical reaction is complete. When it's complete, we call that the equivalence point, which is the concentration of hydroxide ions and the concentration of hydrogen ions for this particular acid and base are equal. We normally involve an indicator in this, which is a substance that changes color, pretty close to where the equivalence point is occurring. And so here's an example of how you might do that titration. You slowly add the base to the unknown acid until that color changes. We use the formula M1V1 equals M2V2. It's not really introduced in this text too much, but it's pretty useful. So the molarity 1 times the volume 1 is equal to the molarity of the second times the volume of the second. And it's nice. You can use it with milliliters or liters or whatever. As long as you know one, you can find the other with the titration. So that's pretty cool. Here they're showing an indicator changes color, pink. Maybe it's phenolphthalein or something like that, but that's fine. The other way to do it is to use, look at the size of this thing, can you believe that? This giant electronic pH meter, which now of course we have from Vernier, which are like the size of a pen and just plug into your laptop, but this would be no need for an indicator necessarily because you can get your pH change electronically recorded, so that's kind of cool. So if you take a strong acid and a strong base, sodium hydroxide is a strong base, hydrochloric is a strong acid, you make water into salt. That's old information for you guys. And really what's going on is hydroxide ions and hydrogen ions are forming water. And so if you take strong acid, strong base, your equivalence point is going to be about 7. So as we add sodium hydroxide, our pH continues to increase, and then you can see over a very small volume added, the pH change is severe, and so we can figure out to get to pH 7 exactly how much sodium hydroxide we need to add. So what if we do a weak acid with a strong base? So sodium hydroxide is our strong base, and acetic acid is pretty weak, and then we get this sodium acetate ion that we've worked with a lot this chapter, it feels like, and water. Well, then you say what's really going on here is we take the hydroxide ions and this weak acid and we make the acetate ion in water. And so our equivalence point is actually going to be above 7. Now, hopefully that makes sense. If you have a weak acid and a really strong base, and bases are higher than 7, then our pH at equivalence is a little higher than 7. And so here we're rewriting this, what happens to our acetate ion then once this acid-base reaction occurs in the beaker. Well, our acetate ion will react with water to become acetic acid again. And so as it produces a little bit of that hydroxide ion, we end up getting a pH that's just a little higher than 7. Here we're at about 8.5 for a weak acid with a strong base. So let's switch around to a strong acid with a weak base. So at this point you're probably thinking to yourself, well, if we follow the same logic as the last slide, our pH should be a little below 7, and you'd be correct. So hydrochloric acid is a very strong acid, and ammonia is a kind of a weak base, and so we can make ammonium chloride. And so what's really happening is the hydrogen ions reacting with NH3 to make ammonium chloride. So our equivalence point's a little below 7, and you can say, well, what's happening to ammonium chloride? I mean, we've worked with this salt before. We know that dissociates into NH4 and Cl-, so it dissociates into NH4+. And if that's in a beaker with water, that thing will give up a hydrogen and become NH3. And hydrogen ions, so as it's releasing more hydrogen ions, we're going to become a little more acidic. And that's why your pH is a little below 7. So it's sort of odd to think about it. It almost has more to do with the salt product than it does with having strong acid, weak bases, but either way you get to the same answer, which is an equivalence point a little below 7. 5.5 or so. So let's look at a problem. How can we do this? We got 100 milliliters of 0.1 molar nitric acid, and they're titrated with 0.1 molar sodium hydroxide. What's the pH? Well, if you have molarity and a volume, you can get to moles. So that's nice. I mean, molarity is moles over liters, so all you have to do is call this 0.1 liters, and we're set there. We can do the same thing here. So let's find out what we have here. We set up our equation saying our HNO2 is reacting with the OH minus from our sodium hydroxide solution. And when it does that, we're going to give a hydrogen up and become NO2 minus and water. And so we're going to say, well, what do we start with? We start with the 0.01. Okay, that's this molarity in milliliters solving for moles. So the 0.1 times the 0.1 is the 0.01. And then we do the same thing with the OH, because there's 100 milliliters of this as well, because this is a monoprotic acid and a base, a strong base, and so we can say those concentrations are going to be the same. And when we end, if we got to the equivalence point, which is, it tells us we did, then we got rid of this acid, we got rid of this base. They reacted to completion. So when they say we're at the equivalence point, we can say we're ending at 0. So it's kind of like ice chart. You can have I, 0.01, 0.01, change, minus 0.01, minus 0.01, end at 0. And so then if we're doing that, what do we increase by? Your change would be plus 0.01 here. And then you could do water, but that's not going to significantly change your pH, so we'll just focus on this guy. And so we get this nitrite ion, which is a 0.01 molar. And we mixed 100 milliliters of this acid with the same concentration of base. So it definitely took 100 milliliters of base as well, because we got it to equivalence. And so if we had 100 milliliters of this acid and 100 milliliters of this base, our final volume in this beaker or this flask is 200 milliliters. So now I can say, okay, my concentration of NO2 is my 0.01 moles divided by my 0.2 liters to get molarity of 0.05 molar. Now, that's great. We found a concentration of what we're producing in the reaction, but our question is for pH. How do you find the pH? Well, you guessed it, we set up another equilibrium chart, and we say, okay, if we made this, because a couple slides ago I said that salt you're producing is probably more important than the reaction going on. That NO2 salt, which is just nitrite, which isn't even truly a salt, it's just an ion right now, is going to mix with water. And that's going to take a hydrogen from water. Water is going to become OH minus, and we're going to make HNO2 aqueous. And so here's what's going to happen. We say, all right, we start with the 0.05 molar of NO2 from this beginning reaction that we calculated. Water is not a big deal when you're doing a reaction with a base. And let's say we're starting with none of this because the HNO2 from problem 1 reacted totally, so we don't have any left in the beaker. So our change is a minus x, a plus x, a plus x. At this point it's looking very familiar, maybe a little post-traumatic stress for you and for me. At equilibrium we're at 0.05 minus x. We're at a positive x and a positive x. And you guessed it, you're going to solve for Kb from your book, and you go and you look up the Kb of NO2 minus and find a value for that. And you set up your products over your reactants like we've done so many times before, and you end up finding your Kb from the book and solving for x. And more than likely you would do this with a quadratic. You could certainly take x out and see if what you solve for x this way, if it's smaller than 5% of 0.05, which it probably will be. That number is really small. So you could probably use an approximation and solve for x that way. And when you solve for x, you'll be getting hydroxide ion concentration. And if we take a negative log of that, we have a POH. And if we subtract that from 14, we have a pH. And 10 minutes and a few gray hairs later, we have answered the problem of what is the pH at the equivalence point. So, holy smokes, right? Doable. It's doable, but it's what a mess. All right, so they used their approximation. They found the hydroxide ion concentration. Down here, they took the negative log of that, like I told you for POH. They subtracted that from 14 to get 8. So 8, and then you can ask yourself, well, great, I spent 10 minutes working on this thing. Does it make sense? What do I have here? I have a kind of a weak acid with a really, what I know to be absolutely a strong base. And I got a pH that's a little basic. So I'd be happy with that logically, kind of working out. Cool. So let's look at indicators. Acid-base indicators, those little things we drop in there that change color when you change the pH. Here we have the acidic form of the indicator, and the conjugate base form of the indicator is what IN stands for. And so if our concentration of the acidic indicator as opposed to the conjugate base is very large, then the color of the acid predominates in the indicator. Hopefully that's really logical. If the concentration of our acidic form of the indicator is very, very small compared to the concentration of the conjugate base form of our indicator, a very, very small number, then the color of the base form of the indicator predominates, which again, hopefully makes a lot of sense. So here's your table for colors of all of these different indicators. We've used phenolphthalein, bromothymol blue are probably our kind of go-to guys in the lab here because they're around that 7 range, which is nice for us. But there are all sorts of pH range indicators that are good for different ranges, and so that's good to know as well. Here's an abstract from red cabbage, which works as an indicator, and as you increase the pH, it changes from a red to a yellow. All right, so if you were to do a strong acid with a strong base, you're going to be equivalent around 7. Here's where your indicators would be effective: thymol blue from 1 to 2, methyl red about 5 to 6.5, phenolphthalein from about 8 to 10. If you're going to do a strong acid with a strong base, you say it's probably going to end up around maybe 7-ish. You might want to stick with methyl red. That'd probably be the best. So we could answer the question using that chart. You have to have the chart, which is what indicator would you use for a titration of an acid with a base. And so you'd find your pH, and then with your pH, you'd look back to that chart and say which is going to change color at close to the pH I expect my reaction to occur at. And so if you took HNO2 with KOH, you'd say, okay, I got kind of a weak acid with what I know to be a pretty strong base. So at the equivalence point, we'll have the conjugate base of a weak acid, and so our pH is going to be a little greater than 7. So if we're going to be a little greater than 7, maybe a cresol red or a phenolphthalein might be the one we want to bet on. And so that's what they're saying as well. So that's great. All right. So now we get to a tough one. Not to discourage you, but it's doable, but it's a little tricky, and that's solubility, which is when will a salt dissolve in solution and stay dissolved, and when will a salt precipitate or fall out of solution and become the solid junk at the bottom of the beaker. So here we look at silver chloride. Excuse me. Dissociates into silver ions and chlorine minus ions, and our KSP is equal to our products over our reactants. But you'll remember in equilibria expressions, we don't write solids and we don't write solvents. And because all solubility problems pretty much start with a solid precipitate, you're not going to have to write these reactants. You really just have to write the stuff that's aqueous. So we say KSP is the concentration of silver and the concentration of chlorine. We call that a solubility product constant. Now, if there were a 2 or a 3 in front of that chlorine, that'd be a squared or a cubed respectively on the chlorine concentration. So don't forget that from solubility stuff we've done before. Oh, here's the example of that. Magnesium fluoride, magnesium and 2 fluorines. And you can see when they write their equilibrium expression, they make that fluoride ion squared. And then here we have silver and carbonate ions, and the silver has the 2 as the coefficient, so the silver will be squared and the carbonate will not. So you're kind of getting the trend here. On and on it goes. We know coefficients go to superscripts. We've done this a little bit before. So if we dissolve an ionic solution in an aqueous solution, and we try to figure out what their concentrations are currently, if we take the current concentrations of these ions, that gives us a Q. Now you've done this before a couple chapters ago and compared it to equilibria. So if Q is quite a bit less than KSP, then we can say the concentrations that we currently have are less than we could hold. So that's unsaturated solution. And we would not form a precipitate in an unsaturated solution because we can still dissolve more solid if we had to. If our Q is about equal to KSP, we say we're saturated. If we're saturated, we're dissolving as much as we can hold at that given temperature, and so we probably shouldn't form a precipitate. Now, if Q, our current concentration of ions, is greater than our KSP, then we have more than we can hold at that temperature. We call that supersaturated. And if you're supersaturated, that's a situation where precipitate will form. So here's the KSPs for just a whole bunch of stuff. In your book, table 16.2, it's pretty useful. Use it a lot for these questions. And it gives you KSPs for all these different deals. So how do we use KSPs to solve problems? You start with molar solubility. Molar solubility is the solubility in moles per liter that a solute can hold in a saturated solution. So solubility is grams per liters. That's normally where they'll start the problem off. And then you got to get it to molar solubility. So we can take our solubility they give us in grams per liters. We can get it to moles per liters with the atomic mass, of course. That'll give us the concentrations of our cations and our anions. And we can use that to find our KSP, because this molar solubility is commonly called S, and we use S to get to KSP. So if we start with KSP, we can work backwards to get to concentrations of cations and anions from that. Then from those we can find our molar solubilities, and then we can go back to grams per liter. So it's kind of like going atoms to moles or moles to atoms. You can take these problems both directions. So let's see if we can figure this out. What if they ask us, what's the solubility of silver chloride in grams per liter? So we want to figure out how many grams of silver chloride we could dissolve in a liter. So we set up our equation. We say, okay, here's solid silver chloride going to ions. And we look up in the books, what's silver chloride? It's KSP, 1.6 times 10 to the negative 10. Okay, cool. So here's our change. We're going to start with no dissolved ions. We're just putting solid silver chloride in this stuff. So as silver chloride starts to dissolve, instead of our minus X plus X plus X, when it's solubility, we go minus S plus S plus S. And because we don't write this guy in KSP equations, we pretty much just leave him alone because we don't deal with the solid a whole lot. So at equilibrium, we have S and S for silver and chlorines. It's just a 1-to-1, so you don't have to do a 2 or 3 or any of that junk down here. You're just set with just a regular old S. And so now I can say, okay, KSP is equal to my concentration of silver ions and chlorine ions. So I can say KSP is equal to S squared. Well, it's pretty easy to solve for S now. If KSP is 1.6 times 10 to the negative 10, I say 1.6 times 10 to the negative 10 is equal to S squared. Take square root of both sides. I get 1.3 times 10 to the negative 5. Now, that's the same thing as saying that's moles per liter solubility. So I can say silver will dissolve 1.3 times 10 to the negative 5 moles per liter. And that's where we're going to stop